In the previous 6 videos, we talked about internals of hash table, ways to implement them and how to gracefully handle collisions. In this video, we put our entire focus on performance and we would look at how to quantify the load on a hash table, the impact of chaining and open addressing on performance, understanding the performance gains and loss for each strategy, and conclude with a very interesting performance optimization. But before we move forward, I'd like to talk to you about a course on system design that I've been running for over a year now. The course is a cohort-based course, which means I won't be rambling a solution and it will not be a monologue. Instead, a small focused group of 50-60 engineers every cohort will be brainstorming systems and designing it together. This way, we build a solid system and learn from each other's experiences. The course to date is enrolled by 600 plus engineers spanning 9 cohorts and 10 countries. Engineers from companies like Google, Microsoft, GitHub, Slack, Facebook, Tesla, Yelp, Flipkart, Dream11 and many more have taken this course and have some wonderful things to say. The coolest part about the course is the depth we go into and the breadth we cover. We cover topics ranging from real-time text communication for Slack to designing our own toy load balancer to ClickBuzz's live text commentary to doing impressions counting at scale for any advertisement business. In all, we would cover roughly 28 questions and the detailed curriculum split week by week can be found on the course page, which is linked in the description down below. So if you're looking to learn system design from the first principles, you will love this course. I have 2 offerings for you. The first one is the live cohort based course which you see on the left side, and the second one is the recorded course which you can see on the right side. The live cohort based course happens every 2 months and it will go on for 8 weeks, while the recorded course contains the recordings from one of the past cohorts as is. If you are in a hurry and want to binge learn system design, I would highly recommend you going for the recorded one. Otherwise, the live cohort is where you can participate and discuss things live with me and the entire cohort and amplify your learnings. The decision is totally up to you. The course details, prerequisites, testimonials can be found on the course page arpitbhayani.me/masterclass, and I would highly recommend you to check that out. I put the link of the course in the description down below. So if you are interested to learn system design, go for it. Check out the link in the description down below, and I hope to see you in my next cohort. So hash tables are amazing data structures and it gives us constant time performance when there are 0 collisions. Internally, it is just an array where when we would want to place a key in the hash table, we pass the key through the hash function, take the index, go to that index, place our key there. Right? It gives us constant time performance when there are 0 collisions. Right? But at scale, that's impossible. You have a large application key range that you are trying to fit into this small space. So there is bound to have collisions. And we know that as hash table gets filled, the performance would degrade. So how do we know that my hash table is full? We need a way to quantify it. So the way through which we quantify this is called as a load factor. So load factor theoretically is alpha, which is equal to n upon m, where n are the total number of elements in your array, in your hash table, divided by the total number of slots in your hash table. So if I'm placing 20 elements in my hash table, where my size of the array is 10, my load factor is 20 upon 10 is equal to 2. Right? So load factor for each strategy, like the definition of load factor would not change. But let's just take a look on how load factor is there for chaining and open addressing. We'll talk about chaining first. With chaining, we can clearly see that we can never fill the table. A table will never get full, because with chaining, you're always adding the key that you're inserting in the new slot, or rather in the new node of a linked list. Right? You're always creating a new node and putting it there. So you're always using an auxiliary data structure to hold the key. This way, even if there is collision, even if there is anything, you are just adding a new node to the linked list. So your table, although you may occupy all the slots of your hash table, but you would never be able to fill it completely. But obviously, when you add a large number of keys, even with chained hashing, your performance would start to degrade and that would be worrisome for you. With open addressing, you would eventually fill the table, because what you are doing is you have an array where you are trying to place a key. If that slot is occupied, you are finding the next free slot in your hash table. And with time, the entire hash table array that you have will be filled. Right? So when your entire table gets filled, there would not be any place for you to place a new key, right? Which is what your then your writes would start to fail, right? So you would be running out of your space eventually. So that is where it is very important for you to measure how full the table is and then take preventive measures of your hash table still performing really well, right? So with chained hashing, if I talk about the formula, load factor, it can simply be put as the average number of elements that you are storing per linked list. Again, the formula still remains the same. You just go through linked list by linked list, count the number of elements that you have, take the average of it, you get chained hashing, right? So if alpha is the load factor in case of your chained hash table, the time to resolve conflict would be a big O of 1 plus alpha, right? 1 to add the new node and alpha, which is to traverse the list and resolve the conflict. So your overall time to resolve conflict, overall time to resolve a collision with chained hashing would be order of 1 plus alpha. And it's very easy, like, because that's very straightforward to look at. But with open addressing, things become a little complicated. Because with open addressing, what you are doing is when we are trying to do any theoretical analysis on open addressing, here your collision interfere with each other. Because your collisions on one slot will interfere with the probe that begins on another. For example, if I have 3 keys K1, K2, K3, say K1 and K2 gets hashed to index 0, right? So I inserted K1, it went to index 0. Then I inserted K2. K2 also hashed at, K1 hashed at index 2. I placed K1 at index 2. I took K2 and hashed it. It also spit out 2. So I'm trying to put K2 in the slot 2, but that is occupied by K1. So I'll find the next available slot. I found slot 3 to be available. So I placed my K2 at 3. But now my K3 came in, that got hashed at 3, right? But the slot 3 is occupied by K2. So then K3 would have to move forward, right? So here you see, with this kind of situation where your collisions interfere with other places, it's hard to do a theoretical analysis, but still researchers have done a fairly great job at doing that. But just that we would not dive into the theoretical analysis of that part, but rather stick to more of a practical approach that would help us build our own hash table, right? So two common ways to handle collisions with open addressing. First is linear probing and second is quadratic hashing. So now if I talk about it, that how would the number of probes is equal to, upon collision, how many times would I have to move forward to find the next slot? If I plot that against your hits and misses for linear probing and open and basically double hashing, what we see is an exponential rise in the number of probes required for us to find an empty slot or to do a key lookup, right? So as your table gets filled, the number of collisions or the number of probes, not collisions, the number of probes that you would have to make in order to find an empty slot would be exponentially increasing, right? Linear probing performs very poorly as compared to double hashing, because with linear probing, you have a problem of clustered collisions and you will do far more lookups because of a poor hash function. But with double hashing, you are using 2 hash functions. So its performance is a little better than what linear probing would give you, right? But in both the cases, we are just thinking about it also depends on the implementation, but the worst case is you would do an entire table scan. So it is upper bounded when there are no infinite loops. In your probing function, your upper bound is limited by the number of slots of your array. So that is still the worst case. But if you stuck in an infinite loop because of your probing technique, because of your hash function, then it might go for a big toss, right? But in any case, as your load factor increases, what would happen? The number of probes required for you to do a key lookup or find an empty slot to insert or find a key to delete it would increase exponentially, right? Okay, so now given this, which one is the best strategy then? Because when we talk about performance, there has to be performance metrics that we are taking a look at to find out, hey, given load factors, given the way we are storing the data, which strategy should I be picking, right? So depending on the probing strategy, here, one thing that we all should remember is the cost of a single probe. It matters a lot, right? When I say a single probe, so for example, how am I going from one place? With open addressing, what you are doing? If one slot is filled, you're finding the next slot, right? How costly it is for you to find the next slot, right? That is very important. So let's take a look. So first, probing is costly with chained hashing for two reasons. First, you have to do linear traversal of a linked list, right? So for example, if you are doing a key lookup, you went to a particular index. If that is filled, you go to, and then you start iterating through the linked list one by one to eventually find your particular key. So this is very costly for a chained hashing, because each probe requires you to do a random access of your memory, because your node can be allocated anywhere in the heap. You are doing random access, and which is definitely not cache friendly, because when I say cache friendly, it's CPU cache friendly, right? So when you are reading a particular page in memory, you are bringing in a contiguous location of memory in your CPU cache. So if your slots or if your linked list nodes are placed together, then it would be much efficient for your CPU, because it would not have to go to RAM to access it, but rather from CPU cache itself it can access it. So probing is costly with chained hashing purely because your linked list nodes can be allocated anywhere in the heap. So you're doing a random lookup in your memory and random jumps in your memory that would slow down the performance, right? Because you are not using CPU cache well, right? With double hashing, it requires us to evaluate two hash functions. So double hashing, you might think, hey, then double hashing, is that better? Double hashing seems very better, but two major bloopers there. First is it is very CPU intensive and time consuming. Evaluating a hash function takes time, takes CPU cycles to do it, and it's very intensive, right? So that is why you are sacrificing on the time a bit to say, hey, at least my table would be very well used and I would see very fewer clustered collisions, right? But it suffers from another problem, that double hashing is also not cache friendly, because with double hashing what you are doing is in the entire hash table, you are jumping from one slot to another slot that might be really far away. Again, this is not cache friendly. But again, same thing. Your blocks are fetched together and placed in your CPU cache when you're accessing an array. The next, because you are jumping within the hash table by taking longer leaps, the next index that you might access in your array might not be present in the CPU cache, requiring you to go to RAM, get the data and access it. So also not cache friendly. Now here, this is how you should be thinking about it, right? Which strategy would you pick to implement hash table? You have to understand the pros and the cons literally at the operating system level in order for you to make the best decision call, right? So which one is the optimal strategy then? It depends on the use case. Just like system design, just like most of the things in real world, everything is a trade-off, right? So depending on the use case that you have, there is no one optimal strategy to do it, right? It depends on how your application is structured, how your application is going to exploit the data, how your application is going to access the hash table. It depends on that, which strategy would you choose. But you should be aware of the pros and the cons of each of the strategy and how you are and see which one fits your use case best. So it's better that if you practice, or if you have a particular use case in mind that you are trying your hash table for, apply all sorts of probing techniques and tune it, benchmark it against the load and see which one performs the best, right? And that is how you should be thinking about it. Now comes the question, how to compare and benchmark? So if you are figuring out a hash table for your use case, or tuning your hash table for the best performance out there, or you are building your own hash table, it is important to understand how good you did, right? How good your implementation is, or how good your tuning is. In either case, there is one thing that you would measure, which is lookup time. Lookup time as a function of load. So how long does it take for you to do a key lookup as the load on your hash table increases, right? This is what is the ultimate metric that you would be measuring when you are ever benchmarking, right? So for your strategy, if you are implementing your own hash table, your own strategy, for your strategy, see how your hash table lookups change when your hash table load increases. So lookup time versus load, right? Measure that. If you're benchmarking existing strategy or tuning parameters to do it, this is the ultimate metric that you have to measure and monitor. So how do you do that? A very simple, if I take about a very simple use case or a very simple generic use case to benchmark it, is simple. Create a hash table of size 1024, insert n elements varying from 32 to 900 and look up 1000 random keys with a high miss ratio. If you do this over and over a million or a billion times, you would see how your lookup time changes with load. And it's a very simple way, and this is something that I found in couple of research papers, which is why in most papers I found this exact same example. So I'm just taking it as is. I still don't know reason why 1024, 32, 900. I might find it when I start implementing my own hash table, but this is how you should be thinking about it, right? So a very simple benchmarking strategy would give you how good your hash table implementation is for your particular use case. But again, it depends on the use case on how big your hash table is going to be, but do this. It's very simple to benchmark and find the best performance for your hash table, right? So few things that we would see when we are measuring lookups versus load. First is performance for open addressing technique degrades as alpha tends to 1. Right. So if you are implementing an open addressing strategy for your hash table collision resolution, you would see that as alpha tends to 1, your performance start to degrade, because alpha tends to 1 implies the number of elements is almost equal to the number of slots of your array. So you would do a lot of lookups in order to find your key or in order to find your slot, in order to find an empty slot. You do a lot of traversal within the array. So your performance for your open addressing would start to degrade as alpha tends to 1. Second, your chained approach will degrade gracefully, because you are with chained approach, with chained hashing, you are always adding it to an auxiliary data structure. So your performance would not degrade drastically, because you still have enough space you have almost infinite, not really infinite, you almost have a good amount of auxiliary space available for you to put it. You are not bounded by the slots of the hash table. So your performance would not degrade. It would degrade because the lookups would increase, the time would increase, but it would degrade gracefully as compared to open addressing. Third, linear probing would be slower than double hashing. It is always true. Linear probing would be slower than double hashing because double hashing makes you jump here and there. It does not have large number of clustered collisions. Linear probing sees clustered collisions, so your lookup time increases when you are having large number of collisions for a slot for linear probing. So linear probing would be slower than double hashing in almost all the cases because of clustered collisions. And fourth, probes of double hashing would be shorter, right? So with double hashing, because you are almost leveraging the entire hash table slots that you have, the number of probes per collision would be much shorter as compared to linear probing, right? Very clear. So depending on the strategy that you are using, this is what you should be observing. So now with this, whenever you are tuning your hash table, so you can keep those things in mind so that you don't do some random benchmarks to pick the best one for your implementation, right? Now with this, you might think, chain hashing looks much better than open addressing, doesn't it? Right? But it has, it gives you auxiliary data structure to store the keys and whatnot. The performance degrades gracefully. Open addressing is limited by the number of slots of your hash table. So looks like chain hashing is a very good approach, but it is not cache friendly, right? So if you are looking at a very high performance hash table, chain hashing might not be the best way to do so, because chain hashing is not cache friendly, because again you are jumping here and there in the memory, because a linked list node can be allocated anywhere. So it is not CPU cache friendly. You have to do always a memory lookup, right? But when the tables are short, we don't see an impact, right? But when tables go large and the number of collisions increase, your chain hashing would start to suffer, right? Again, everything has advantages and disadvantages, but you have to be aware which one are you picking and why, right? Okay, one very interesting optimization as part of our conclusion. The interesting optimization is how do you get, up until if you think about it, we spoke about so much about chain hashing not cache friendly, chain hashing not cache friendly. There is a very interesting hack that makes it cache friendly. And that is, how about we leverage cache for chain hashing? And when I say cache, it's about CPU cache. How about instead of allocating one new linked list node every time, we allocate it in chunk. For example, imagine it is a linked list of arrays. Right? Think about it. It's a linked list of arrays. So upon a collision, so you have a hash table array. For each slot of a hash table, you are creating linked list of arrays. So that array might be of size, let's say 16. Right? And in 16, you might say you might fit in 2 nodes of a linked list, right? So you're, instead of allocating the memory of a memory equivalent to 1 node of a linked list, you're allocating memory of 3 or 4 or 5 nodes of a linked list. So that is your common allocation. So now what would happen? Because you're allocating that large chunk of memory in one shot, the elements that you're putting in that array or in that allocation would be closer to each other. So when you are accessing them, there is a very high chance that the entire slot will be cached on the CPU. This way, when you are traversing through the linked list, you are still iterating through the array, right? Because they are contiguously allocated. Given that, you can leverage CPU cache, and that is such a beautiful optimization. Yeah, hacks always exist, and this is one of the most brilliant hacks that I have seen to make chain hashing, which is supposedly very poor on CPU cache, make it cache friendly. Such a beautiful technique, and I loved it when I was going through that paper. I'm like, oh God, this is such an interesting optimization, right? So just to gist it out, instead of allocating memory for one node of a linked list, do it for multiple nodes in one malloc call. When you do that, the 3 or 4 linked list nodes that you are trying to fit in there, all of them would be allocated together contiguously in RAM. So when you are accessing one, others would be present in the CPU cache, making your chain hashing cache friendly and iterations faster, right? Okay, so this is a very interesting optimization on chain hashing to make it cache friendly. Now, if your hash table performance matters a lot for your use case, if it is very critical for your application, always remember, experiment with different strategies, parameters and algorithms for your workload and see how it performs. And surely for a small use case, for a trivial web application, you might think it's an overkill, right? But think about it. If it's very critical for your application, for your hash tables to be performant, you have to tune, you have to experiment, you have to try out different strategies, parameters and algorithms to get the best, because that is the most critical part of your application / use case, right? So if your situation is like this, benchmark your strategy and see which one fits your use case really well, right? So that's one thing that you should take away from this discussion, that trade-offs, just like in system design, hash tables implementation, when you have multiple algorithms, multiple strategies, probing techniques, everything is a trade-off. And which one would you pick, why and where? You can only get it from a data-driven approach, which is where you have to do a performance benchmarking and see how it performs well. If you're ever interested in implementing a hash table, this would also help you in thinking how you would test if your algorithm or probing technique that you think is new performs well against the existing strategies, right? So keep those things in mind and let's try to get the best performance out of our hash table implementations. Nice. So yeah, that's it about performance of hash tables. We understood everything is a trade-off. Chain hashing, open addressing, we talked about when one works well, when other doesn't, how to make things cache friendly, and how important CPU level caching is when you're thinking about contiguous memory allocations and all of that stuff. I hope that was amusing and fascinating for you. So yeah, that's it for this video. If you guys like this video, give this video a thumbs up. If you guys like the channel, give this channel a sub. This was the 7th video in the hash table internal series, and I'll see you in the next one. Thanks a ton.